My name is Joanna Boyer, and this is a presentation for Harvard course CSCI-E89, Deep Learning. My topic is a case study in finance in which I explore the use of variational autoencoders to generate simulation paths for financial time series. The main goal of the project is to simulate patterns that are similar but not identical to historical realizations. Having good simulation scenarios that cover relevant potential future realizations of various stochastic processes is of great importance across many areas in finance, including valuation, risk management, testing and analysis of portfolio behaviors, and trading strategies. Backtesting is commonly used to analyze performance on historical data. A common mistake is to rely entirely on backtesting, meaning to demonstrate that a strategy performs well on a selected time interval in the past by replaying history. As we all know, history hardly ever repeats itself, and so it is important to have a set of testing scenarios that capture a richer set of possible market evolutions beyond what actually happened in the past. The data set used in this illustration was downloaded from the Federal Reserve Bank of St. Louis and pertains to the U.S. 10-year swap rate time series between July 2000 and October 2016. The rate is available as a daily observation for each business day in this time interval. There are roughly 4,000 observations in total. An interesting feature of financial time series in general is that the amount of data available per series when daily or coarser observations are used is relatively small compared to the millions of samples available to train deep learning networks for other applications. For the purpose of this analysis, I worked with daily changes in the 10-year rate, which I have aggregated into weekly runs of 5 business days each. The idea is to learn such weekly patterns to synthesize paths that are similar to the historical realization. In addition to learning patterns for the full data set, I also explore the ability to generate patterns for prescribed market regimes such as high rate high volatility, low rate high volatility, high rate low volatility, and low rate low volatility. To designate high or low, I use the average rate and the average volatility over the entire period as thresholds. Regimes are labeled 1 through 4, and the label has been added as the last column in the input data. A 5th regime has also been included for the weekly runs to characterize the weeks in which at least one regime switch occurs. For the purpose of this presentation, however, the 4 main regimes are illustrated. Variational autoencoders belong to the class of generative models, which in turn constitute a broad area of machine learning dealing with models of distributions of points in potentially high-dimensional spaces. In this case, I explore weekly patterns, which are samples in 5-dimensional space, but longer sequences could be explored and the dimension of the input space would increase accordingly. Variational autoencoders seem like ideal candidates to synthesize latent distributions in financial time series. A typical variational autoencoder is defined in terms of a pair of models, an encoder and a decoder, as well as a loss function. The encoder takes the input, in this case a weekly run, which is a sample in 5-dimensional space, and outputs an encoding of this point into a latent representation space, 2-dimensional in this example. In the case of the variational autoencoder, the latent space is stochastic and the encoder actually outputs parameters of a distribution, normal in this case, from which we can later sample to generate new weekly runs. The decoder generates a latent vector by sampling from the distribution and proceeds to develop a reconstruction of the original input. The loss function being optimized during training consists of 2 parts: a mean squared error term that quantifies similarity to the input in L2 norm, and a Kullback-Leibler divergence component that quantifies similarity in distribution between the input samples and the generated ones. One shortcoming of vanilla variational autoencoders is that they offer little or no control over the data generation process. This is problematic if we want to generate specific types of samples, like for example ones that correspond to a high-rate, high-volatility market regime and none other. To solve this problem, conditional variational autoencoders were introduced to model latent variable distributions conditional on other random variables like regime type. In this case, the regime labels can be used for this purpose. Let's have a look at the code. For this work, I modified the variational autoencoder that comes with the Keras documentation to work with weekly run samples and to add conditioning on market regime as previously described. First, we input the necessary modules, including Keras, NumPy, and matplotlib for visualization of results. Next, we load the data from the CSV file into arrays, which are then fed as inputs to the train test split function to separate training from the validation data. We can actually visualize what the data looks like. In green, we have the time series of the daily changes in the 10-year swap rate, and in orange, we have the regimes as coded by their labels, 1, 2, 3, and 4, shown on the right axis. For example, the beginning period starting in July 2000 is a period of relatively low volatility when rates are high, so the corresponding regime is 3. This is followed by regime 1 of higher rates and higher volatility. Then the market returns to regime 3 briefly, then back to 1, and so on. Next, the autoencoder is built inside the build models function. As already explained, it consists of an encoder and a decoder, and the loss function consists of a mean square error part and a Kullback-Leibler divergence part. We are now ready for model training. In this case, the model has already been trained to avoid waiting during the video recording. The total training time for this example is less than 5 minutes on a local CPU. For each regime, we can see the outputs of the training, its history. We can also plot the parameters of the corresponding latent distribution. We can see some of the newly generated sample paths within a given regime. And we can quickly note that these paths look pretty similar within a given regime, but then when we scroll to other regimes, we'll see that they look quite a bit different from this regime. So we have similarity intra-regime and differences inter-regime, which seems to be consistent with our hypothesis that different regimes may have different path distributions. Of course, more rigorous analysis on the significance of this difference is necessary, and it's not included in this example. And then we can also see the training and validation loss as they progress over time. So let's quickly scroll through the other results. The function plot results serves a dual purpose. It uses the encoder prediction function to generate new latent vectors using the test set as input, and it displays associated images like the ones I just shown, like distributions in latent space, the synthesized weekly moves, and the performance graphs. We can also visualize all regimes together on the same plot of the latent distribution. You see the latent mean and the latent log variance. And different regimes are colored with different colors. And we can see some degree of clustering in latent space corresponding to these regimes. Here's another example of path segments generated starting with day 3500 in the data series. I randomly picked this date for illustration. The actual historical path is shown in red, and the new paths are shown in blue. And last but not least, we can use the weekly patterns to synthesize full paths. One challenge is to constrain the full path to stay relatively close to the historical one, or to stay between economically meaningful limits. It should not reach extremely negative levels, and it should also not have extremely high levels that are practically unobservable in reality. To enforce such properties, I introduced a similarity interval parameter, which is expressed in the number of days that a new path can freely evolve before it is constrained to return to actual. In this example, we're talking about 10 business days or 2 weeks. This graph shows, once again, the historical path in red and 50 newly generated paths in blue. In conclusion, variational autoencoders show good promise for the synthesis of simulation paths. However, more work is needed to better quantify generated path properties and to enforce global constraints. The appeal of using variational autoencoders lies in the fact that they are capable of uncovering latent probabilistic parametrizations automatically. They also offer several avenues for further exploration, as they can be extended to work with different families of distributions and can also be adapted to higher dimensional inputs, like biweekly or monthly runs. The main drawback in this approach lies in the difficulty to aggregate weekly patterns into full paths while obeying global constraints. Thank you for watching.